The Y14.5 standard has always talked about controlling centers, center points, axes, and center planes. It also talks about calculating additional tolerance, bonus tolerance, and datum shift, depending on what the standard calls the produced size of the features when MMC or LMC is applied. In the past, the problem was that it was never clear how to determine the correct size or center to use. When inspecting a part, there are lots of different ways to find the center or size. On this hole, I could use calipers, a coordinate measuring machine, I could use a gauge pin, and the list goes on. Unless the part is perfect in form and orientation, these methods can all give you different answers. The 2009 revision of the standard clears this all up by defining several envelopes which are used to determine centers and size for calculating bonus and datum shift. At first, these might seem confusing, so to clear it up, we've created a reference card and models to explain the various envelopes. An unrelated actual mating envelope, like this pin, and its axis, would be used to establish a primary datum or to find the position of this hole. However, a related actual mating envelope, meaning related to another datum, is used for a secondary or tertiary datum feature to establish datums and calculate datum shift, where these datum features were modified with the M or L in a circle. If you're not using these envelopes, you may be introducing too much uncertainty into your inspection results. Techie's envelope reference card and models should clear this all up for you. You'll find more information on these envelopes on our premium site. And in case you were wondering, everything I show in these tips, I can back up with the standard because, yeah, you guessed it. At Techie's, GD&T rules. I'll see you next tip. The subject of this month's tip really gets me going. I would tear my hair out over this subject if I had any hair. People are still using plus-minus tolerance dimensions to locate features. I'm really growing weary of explaining all the pitfalls of this approach. Look, the drawing drives the entire process. When the drawing is unclear, it affects purchasing, tooling, quality plans, assembly, inspection software, tolerance analysis software, and the list just keeps going. The Y14.5 standard has proved that it can give you a drawing with one clear meaning when applied correctly. I just don't understand where this resistance continues to come from when I suggest following the ASME Y14.5 standard. It's really not that tough. In fact, it can be as easy as 1, 2, 3, and sometimes 4. On nearly all of your parts, you need to establish origins of measurement. We do that by selecting datum features that are used to establish datums. Because these datum features are features, they need to be controlled, so we put tolerances on those features, and that's really been clarified in the 2009 revision of the standard. Now, once we establish these origins of measurement, we need to locate everybody else. And you might say, oh, I don't care where that feature is in the part. Well, if you don't care, get rid of it. Every feature costs money. If it's not a critical feature, give it a big locating tolerance. And if it is a critical feature, you're going to indicate that with a tighter tolerance. And then, sometimes, only if necessary, do we add auxiliary datum reference frames and refinements to the locating controls for geometric tolerancing. So, we have 4 characteristics. In general, they are location, orientation, size, and form, but just like in real estate, the most critical of those is location. So, once again, we establish our datums, we control the datum features, and then we have to locate everybody else. So the question becomes, how should I tolerance the location of these other features? Well, not with plus-minus tolerance dimensions. Get over that, will you? Every feature on a part has a surface or surfaces, and there's only one geometric tolerance that can, in one clear way, locate surfaces, and that's profile of a surface. Now, the profile can be a general tolerance, or it can be right up on the field of the drawing. However, we do have some special features. We call them features of size, and those features can establish a center plane, axis, and for those we can use position to control where the center is, like the center of a hole. And with position, we can use the maximum material condition if we're worried about fit and free assembly, or least material condition modifier if we want to make sure we have material for some reason, like the part's going to be machined later on. And there are these special features that are cylinders that happen to be coaxial to a datum axis. You run into these mainly with parts that are made on a lathe. And we can still use position or profile on them, or we can control where they are using the runout tolerances. This drawing shows examples of some of these controls. I have a groove that I've defined with basic dimensions. I have a basic 17 locating it from my datum reference frame from my origins established by A and B. I have a diameter defining how deep the groove is, which is basic, 48. And then I have a basic radius of 4. So I've defined where the ideal groove would be, and then this profile tolerance tells me how much the surface can actually deviate from that true profile. It can go in 0.08 or out 0.08, a total of 0.16. Here I have a position tolerance, and this would have been locating or controlling the axis of the cylinder if I hadn't added the maximum material condition modifier. Now this is saying there is a boundary that the surface cannot violate because I probably want this to fit down into something. And then we have this runout tolerance. Could have been circular, happens to be total with the 2 arrows. And it's saying I want to check the surface to make sure it's not varying too much relative to this axis. So it's picking up form variation, changes in size, and if it's not centered. So kind of indirectly, this runout is keeping the cylinder centered on the datum axis. That's it. It's really not that tough to control the location of your features. This is today's print reading. As an engineer, I want to know that the document I am approving has one clear meaning. If your suppliers do not know how to read a drawing, it's time to look for a new supplier. If you need help with any of this, contact Techies, because at Techies, GD&T rules. I'll see you next tip. The way we do things is changing. Those boxes on the drawing are called feature control frames. The tolerances in those boxes apply to features, not dimensions. In other words, GD&T takes the tolerance off the dimension and puts it on the thing we can touch and measure, the feature. So, when you measure a geometric tolerance, you should be reporting deviations on the feature, not dimensions. This really seems to trouble folks, especially with profile tolerancing. This month's tip explains how to report the results when inspecting a profile tolerance. On this part, datum feature A is these 2 bottom surfaces, and this top surface is to be located 18 millimeters from the plane established by A. The tolerance is a profile of a surface tolerance of 0.3, which means the surface can be up or down half of that tolerance, because the number in the box is always total, and it's implied centered on the basic surface. To inspect this part, I might use a stack of gauge blocks 18 millimeters high, zero an indicator at the top of those gauge blocks, then run the indicator back and forth and front to back, looking for the high and low readings. On this example, we had a negative or low reading of 0.12 millimeters and a positive reading of 0.04. Now, in an inspection report to help out process, I would want to report both of these deviations, the highest and the lowest. In addition, though, engineering often wants a number that they can compare to the number stated on the drawing. Imagine that I close in on this surface with 2 parallel planes that remain centered at the basic location. I'm trying to squeeze these planes together to contain all of the surface. When I did that, I made contact with this lowest point, which was the greatest deviation. Since the tolerance zone has to be centered, if I want to compare the deviation in the part to the stated value, in other words, an apples-to-apples comparison, I would double the largest deviation to determine the width of a tolerance zone needed for this part to be acceptable. If that value is less than the value stated in the feature control frame, then I have a part that passed inspection. We are seeing more and more use of profile tolerancing and even reduced dimension drawings. How you fill out an inspection report must change if you want to follow the standard. We can help with this because at Techies, GD&T rules. I'll see you next tip. Datum shift, or displacement, is one of those concepts that requires a lot of thought to thoroughly grasp. The shift that may occur is dependent on the part geometry. So I've decided to make this tip with yet another example of this shift. This topic ties into other concepts like simultaneous requirements and the candidate datum set or rocking datum features. The June 29, 2012 one-hour-long brown bag session is devoted to how these concepts relate. If you missed the broadcast, as with our other brown bag sessions, you may view the video at your leisure if you are a premium site member. Now, here's the tip. As I mentioned, datum feature shift, or displacement as the standard calls it, changes with part geometry. On this part, our primary datum feature is the bottom surface, and so in a setup I would set that against a plate, a very flat plate, to establish my primary or first datum plane. My secondary datum feature is this width, B. Its size is 50.8 plus or minus 0.2, so the largest it can be is 51. And at 51, it can be out of perpendicular 0.3, so it can act like 51.3. In other words, its maximum material boundary with respect to the first datum plane would be 51.3. So if I build a fixture to hold this part, I would have two parallel planes 51.3 millimeters apart. Then datum feature C is this back surface. So it has to come up against a plane that's at right angles to the first planes that I've established using A and B. Let's take a look at two different parts in the fixture or setup for this part, where B has been modified at the maximum material boundary, as you see in these feature control frames. On this part, datum feature B is at its largest size, and it has deviation in perpendicularity that causes it to fill the datum simulator, so there is no datum shift. This part is down near the smallest width, and it has very good perpendicularity, so we are allowed to shift the part up and down in the fixture to bring the holes into their position tolerance. The part has to stay against datum feature A, which is this surface, so there's no shift in that direction, and it has to stay against datum feature C, so no shift left-right. The only shift allowed is up-down if the part is made smaller than the maximum material boundary of datum feature B. Be sure to view the other tips and videos related to datum shift. Some people choose to ignore it, but you really can't because shift happens. As always, if you need help with this or other GD&T topics, give Techies a call because we all know that at Techies, GD&T rules. I'll see you next tip. Because there continues to be considerable confusion regarding composite position tolerancing, I thought I should put together a series of 3 tips that explain position tolerancing from one segment to 4 segment composite tolerancing. I encourage you to view all 3 tips in order from the simplest to the most complex position tolerance. I'm going to use this part to help explain composite tolerancing. Now initially on this drawing we don't see any composite tolerancing. I do have a position tolerance on the 2 holes, Some people might say, well, isn't that really one hole? Maybe I created them at the same time by drilling, but the answer is no. As far as the standard is concerned, these are two individual features, unless I do something to tie them together, which we'll see shortly. So these two holes, 2x, have to be positioned within 0.4 when they're made at their smallest size, their maximum material condition size, with respect to the datum planes established by datum feature A, and so that would be a plane down here off that surface, and datum feature B. Since B is associated with the size dimension, that gives me a center plane that we see right here. And that may be fine for the application. Let's take a look at it though. Here's our 0.4 tolerance zone, and I'm using these little center lines to represent possible axes of the two holes. So what this is saying is these holes can move around within that 0.4 zone, and they can also tilt relative to the plane established by A and the plane established by datum feature B. Notice that they're acting individually. If I wanted the two holes to act like one hole, I would have to tie them together in one of two methods. One way is to use the CF symbol. Now this is new to 2009, and it says treat the two as though they were one continuous feature. So now I'm showing you an axis that would be the axis of the two holes acting as one. The other approach is to use composite tolerancing. So here we have one symbol but two segments to the tolerance. The 0.4 is locating the holes on the part somewhere, and then the 0 at maximum material condition is working just like Rule 1 would on an individual feature. It is saying that if these holes are made at their smallest, they would have to be right in line. As they're made a little bit bigger, they could be misaligned by a small amount. So these holes are kept in line, but now they can float around within the 0.4 zone. So together they can tip with respect to the plane established by A or the plane established by B, and they can move around within that 0.4 zone as we see over in this view. In the next tip, I'll show you how we can start restricting some of this orientation or tilt that you're seeing. Composite tolerancing is a very useful tool. There definitely are designs that need this concept. If you don't like how composite tolerancing works, ask yourself, how would you state the requirement without composite tolerancing? Not all GD&T is intuitive. It is a language that requires some study, but it is today's print reading. If you're going to create or read engineering drawings, you must understand the language. If you need help learning this language, contact us, because at Techies, GD&T rules. This is the second tip in a three-part series of tips on composite position tolerancing. In this tip, we will see the effect of repeating the primary datum feature reference in the lower segment of a position tolerance. In the first tip, we started with a position tolerance on these two holes that are shown coaxial on the drawing. But if we looked at what could actually happen to each one of these holes with this position tolerance of 0.4, we saw that the axes of the holes individually can tip around quite a bit. So they didn't stay in line by more than 0.4. By adding a composite tolerance or using the continuous feature symbol, either one would work, but we were going to focus on composite tolerancing. So by using composite tolerancing, which means you have one symbol but multiple segments or multiple tolerances, we were able to keep the two holes in line. So this is saying the two holes have to be in position within 0 if they're made at their smallest size. As they get bigger, they can misalign a little bit. But let's say I was assembling a shaft in here, that would assure assemblability. So that was in our first tip. So once again, composite tolerancing, one symbol but multiple tolerances. And the rule is that that upper segment is locating the features on the part. Any subsequent segments' main purpose is to tie the features together in the pattern, to hitch them together, if you will. So in the second tip, we're going to add another layer to this composite tolerancing. Because in the last example, we tied the holes together, but since there was no datum reference, they could be out of parallel to the plane established by the primary datum feature A by as much as 0.4, and also out of parallel to the plane established by the secondary datum feature by as much as 0.4. So by adding this segment, we are now tightening up the orientation. So the rule for composite is that the first time you see datum feature references in an upper segment, they're there to control the location of the feature. If I repeat the datum feature in subsequent segments, in lower segments, then I am tightening up the orientation. So in this case, the zero tolerance is controlling the axes of the two holes with respect to one another. The 0.25 is limiting how much that axis then can be out of parallel to the plane established by the primary datum feature. But since it's an orientation tolerance, it still allows this axis to float around. That's why we need that upper segment to locate. So you'll see that this 0.4 is a cylindrical zone, shown over here in this view, and here's a side view of the cylindrical tolerance zones. And that limits where this axis can be with respect to the datums, or the origins, on this part. So if I animate this, I think you can see it a little bit better. The axes cannot go outside of the 0.4, and because of the second segment that we've added, the axes cannot tip more than 0.25 with respect to that plane established by our primary datum feature A. Since I didn't repeat B, I could have, but since I didn't repeat it, you'll notice that the axes can be out of parallel as much as 0.4 with respect to the datum plane established by datum feature B. In our next tip in this series, we're going to add another segment here, and we're going to bring down datum feature B to show how we can restrict the orientation relative to both datum planes. Still struggling with GD&T? Give us a call, because at Techies, GD&T rules. I'll see you next time. In this third and final tip on composite position tolerancing, we will look at the effect of repeating the primary and secondary datum feature references in the lower segments of a composite tolerance. Whoa, you might think this is overkill of composite tolerancing, but we have had customers that required this level of control. Let's walk through it. Remember that the lowest segment of a composite tolerance, in fact, any of these three segments, main purpose is to control the holes better to each other. If I repeat the datums, they're there for orientation only. So this last one is the tightest refinement on controlling the location of the holes to one another. Keep them in line. This segment, since it references A, means that the holes have to remain parallel to A within 0.1. The diameter symbol is here because it also is controlling the holes with respect to one another. If we didn't have this lowest segment, this would be the one keeping them coaxial, and that is the cylindrical tolerance zone. The same is true for this one, but now we've repeated both A and B. So what we're trying to do is keep the pattern of holes parallel to the plane established by A and B, in other words, the second plane of the datum reference frame. And the upper segment is controlling the location on the part of these two holes relative to the datum reference frame. So if I animate this, the holes have to stay in line, as you can see down in this view. They're allowed to float within the 0.4 relative to A, but they have to remain parallel within 0.1. If we look in this view, we're seeing the plane established by A and B. And the holes have to remain parallel in this view within 0.25, as well as staying in line with each other. And to make sure that the holes don't float off the part, we have the position of 0.4, which is locating the holes, and we see that down in this lower view. so the holes are free to float around within the point 4 as long as they stay in line with each other, remain parallel to the plane established by datum feature A within point 1, and parallel to the plane established by datum features A and B within point 25. Like it or not, this is how to control location and orientation of patterns of features. The more you use composite tolerancing, the easier it will be. If you need help getting started, contact us, because at Techies, GD&T rules. I'll see you next step. The April 2012 through June 2012 tips explain the meaning of 2, 3, and 4 segment composite position tolerances. A composite tolerance has one geometric characteristic symbol but multiple segments. These next 3 tips will show sample gauging that could be used to inspect those composite tolerances. I do not want to suggest that gauging is the only way to inspect composite tolerancing. Some high-end CMM and vision system software can handle composite tolerancing. Also, a technique known as paper gauging or graphical analysis can evaluate the data where composite tolerancing or datum shift is involved, even if you don't have a fancy CMM or optical system and are using surface plate equipment. We cover all these approaches in our inspection course. I use sample hard gauges in these tips because visualizing a gauge often helps folks understand a concept. Composite position tolerancing is used when you want to control the features of a pattern tighter to one another than to the datum reference frame. In this case, we have 2 holes that are shown coaxial on the drawing, and we'd like to keep them coaxial. So the lower segment of this composite tolerance, and you can tell it's composite because we have one symbol but multiple tolerances. And this lower segment is saying that these 2 holes have to be in position 0 at their smallest size, at 1495, with respect to each other, not to any datum references. Since there is no datum feature reference in the lower segment, the coaxiality of these holes may be checked with a simple pin. The next 2 tips in this series will illustrate how a 3 or even 4 segment composite tolerance may be inspected using hard gauging. If you need help with any GD&T concepts, contact us, because at Techies, GD&T rules. I'll see you next tip. The May 2012 tip explained the meaning of a 3-segment composite position tolerance where the primary datum feature was repeated in the second segment. Location of the pattern is controlled by the top segment of a composite tolerance. If datum feature references are repeated in lower segments, they are there to refine the orientation of the pattern of features relative to the datums established by the referenced datum features. Here's a gauge that helps illustrate this concept. The composite tolerance on this drawing was explained in the May 2012 tip. The upper segment locates these 2 holes. The lowest segment is controlling the relationship of the holes to one another. This middle segment is the one that will be illustrated in the gauge. Since datum feature A has been brought down and referenced in this second segment, datum feature references in the lower segments control orientation. So you'll notice that the gauge pins have to remain parallel to the plane established by A as you inspect for this 0.25 positional tolerance. The gauge pin is not confined in location to the plane established by datum feature A. It is, however, confined in orientation, or in this case, parallelism. So you're allowed to move the gauge element up and down to find the spot where it will pass through the 2 holes. The more you use composite tolerancing, the easier it will be. If you need help getting started, contact us, because you know that at Techies, GD&T rules. I'll see you next tip. The The June 2012 tip explained the meaning of a 4-segment composite position tolerance. This may seem a bit extreme, but I have had customers who require this level of control. Keep in mind that datum features referenced in the upper segment of a composite tolerance are there to control the location of the pattern of features. If datum feature references are repeated in lower segments, they are there to refine the orientation only of the pattern relative to the datums established by the referenced datum features. The gauge you're about to see is for inspecting the second segment of this composite position tolerance. Since the datum referencing is there only for orienting the pattern, the gauge elements or pins that are going to check the position of 0.25 have to remain parallel to both datum planes, but be free to move around in location, and you'll see how that's accomplished. The location of the holes will be verified separately to make sure they're in position within 0.4. This gauge is holding the gauge elements parallel to the two datum planes, so the pins can float around as long as they remain parallel. Their size is going to be the smallest size of the holes, which is 15 minus 0.05, then minus the 0.25 position tolerance. As always, if we can help with your GD&T applications, do not hesitate to contact us, because at Techies, you know the GD&T rules. I'll see you next tip. Hey, I'm all for default dimensions, tolerances, and rules, provided they have one clear meaning. In the Y14.5 standard, there are many defaults, such as on a 2D orthographic drawing, a 90-degree angle applies where center lines and lines depicting features are shown at right angles and no angle is specified. Or all tolerances apply to the full depth, length, and width of the feature. A large default profile of a surface tolerance that's related to datum reference frames is a wonderful idea today on drawings. However, many companies use default tolerances that are not clear. One company that I worked with used what they called STAMP. It stood for Standard Tolerancing and Manufacturing Practices. It relied on implied datum features and meaningless rules to determine tolerances. I helped lead an effort to stamp out STAMP. They're now using the Y14.5 standard very effectively. This tip is about default tolerances that do not have one clear meaning. Referencing the Y14.5 standard invokes a whole lot of tolerances that keep our drawings quite simple. In a previous tip, I showed how this drawing and these geometric tolerances default or invoke all of these tolerances that you're seeing in blue. And they all have one clear meaning. In fact, you invoke all of these notes also, so I don't have to put them on the drawing. Now, which would you rather have, the drawing on the right or the drawing on the left? I think we'd all go with the drawing on the right. The reason we've gone to geometric tolerances is to fix the problem that we used to have with those general tolerances. You're all familiar with these linear and angular tolerances that do not relate to the datum reference frame. They allow for tolerance accumulation. We get wedge-shaped tolerance zones because of that angular tolerance. And we end up dimensioning and tolerancing points in space that cannot reproducibly be measured. So because of these and other problems with this general tolerance, we are now seeing companies replacing these with things like the general profile of a surface tolerance to a datum reference frame that has one clear meaning. I still find some companies, though, trying to take some intermediate step. I see companies now referencing ISO 2768. There's a few problems with this. First of all, this standard applies to machined metal parts and may apply also to sheet metal parts. We're told this in the standard right up front. But I find people applying this standard to things like molded plastic parts. In the standard, it says that exceeding the general tolerance should lead to a rejection of the workpiece only if the function is impaired. Who makes that decision? That's pretty subjective. And it's not clear when you look at the tolerances provided in this standard what quality level they're at. Are they at a 3 sigma level or a 6 sigma level? In the standard, they show this sample drawing, a fairly simple drawing, and we're told that if you use the tables, the tolerances that are down here in phantom are implied. So all the stuff in phantom here is implied. On a complex drawing, I don't know how you'd be able to figure out what is implied on these features. And things like, you see datum C here? Datum feature C is that hole. Why couldn't it have been this pair of flats? How did I know to imply that hole as a datum feature? And I could go on and on with those sorts of questions. This standard is an older standard, and it's going to be revised, but I strongly recommend that you just state, using Y14.5, what your requirements of your part are. Usually less than half of the features on a part require tight tolerances. Defaulting to tight general tolerances on the entire part can only increase cost. If you need help replacing your default tolerances with clear, concise defaults, give techies a call, because at techies, you know, GD&T rules. I'll see you next tip. This is another tip on datum displacement or shift. The concept is not well understood by many folks. Too many try to use it as a bonus tolerance, which is wrong. Maybe this tip will clear things up. Once folks have taken a course in geometric tolerancing, they usually have a pretty good understanding of what the maximum material condition modifier means after the tolerance. However, many people remain confused regarding the M, which stands for maximum material boundary, not maximum material condition, that you find sometimes after datum feature references like B and C. Datum feature A is this surface. Datum feature B is this boss. And datum feature C is that slot, which is stopping rotation. But for the point I want to make in this tip, we don't have to think about that. Let's take a look at datum feature B. What is its maximum material boundary? Well, it would be the largest that this boss can be plus its relationship back to A, or its perpendicularity, which happens to be 0 at the largest size in this case, which makes the calculation easier. To understand, though, what this M after the B means or does, it often helps to imagine a hard gauge. First of all, to inspect the feature that has the position tolerance on it, I might have a sleeve that slides up and down. The size of the hole in that sleeve would be the largest that the boss can be, which would be 12 plus 0.2, then plus the geometric tolerance of 0.3. So if this boss comes in smaller, it'll be able to be out of position a little bit more, and that's what the M does for it. It gives us that bonus. Like I said, most people seem to have a pretty good grasp of that. But now, what does the max material boundary modifier after B mean? Well, it doesn't mean that you get more tolerance at the boss. What it does mean is that there's allowable shift at the datum feature. So we have datum feature A is sitting down on this surface, and here's your datum feature B. The way I have the part positioned in the gauge, the sleeve would not fit over the considered feature. However, because of the M after the B, I am allowed a datum shift. So datum feature B's maximum material boundary would be its largest size, 12.3, plus the 0 perpendicularity tolerance. You can't leave that out. I know it's 0 this time. Many times it isn't 0. And so you have to include that. That gives me the size of a hole that I might have in this gauge. The sleeve won't go over the considered feature if I keep datum feature B perfectly centered in this opening, in this hole. But I'm allowed to shift because the M was there. And if I shift the part over, now the sleeve can fit over the boss and the part would pass inspection. If you believe that this M gives you additional tolerance, positional tolerance, Let's say that this boss comes in at 12 or down at 11.7. There's an extra 0.6 shift that you could have total here. If you treat that, though, as a bonus on this considered feature, not only are you saying it can move out of position more, but you're also saying that it could tip more, because orientation is included within position, if you remember the GD&T hierarchy. In this case, that orientation is perpendicularity. So if you were to treat it as a bonus rather than a shift, that means this boss would be allowed to tip more just because the datum feature is smaller. And that would be flat out wrong. We all need to understand this concept because we all know the shift happens. I've even seen it on bumper stickers, although it's spelled wrong. I hope this clears it up. If it doesn't, give us a call, because at Techies, you know that GD&T rules. I'll see you next tip. You know, back when I located features with plus-minus tolerance dimensions, I would spend a tremendous amount of time trying to decide how to place the dimensions to minimize tolerance accumulation. Then others would review the drawing and argue that the dimensions should be placed differently. When basic dimensions are used, this issue goes away. Check out this tip. It is very important to realize that the placement of basic dimensions does not tell you the origin of measurement, nor does it control the relationship of features to each other. There's no tolerance on these basic dimensions, so it really doesn't matter how I place them on the drawing. As we look at these two drawings, this upper one has all of the dimensions coming from the axis of this hole, whereas on the lower drawing, all the dimensions are coming from these two edges, which is something often the shop might prefer. What's the difference between these drawings? Nothing. They have exactly the same meaning, because the origin of measurement is established by the datum features, and when I want a tighter relationship between features, like between these two tapped holes, I've used composite tolerancing to hitch them together and control their relationship tighter. So because A, B, and C have been referenced in all these feature control frames, your origin of measurement is where these three mutually perpendicular datum planes intersect. And as far as the relationship between those M10 millimeter tapped holes goes, even though this is dimensioned at 35 and 130 from the edge of the part, the distance between them is 95, and that's 95 basic. There's no tolerance on that. The tolerance is on the holes themselves, and they can't deviate more than 0.1 relative to each other. Relative to your origin, they can move around 0.3. That's the upper segment. But the lower segment says, hey, with respect to each other, and since I repeated A, the perpendicularity have to be within 0.1. If you think that the placement of basic dimensions determines somehow what your origins of measurement are, or what the relationship between features is, what are you going to do if you start seeing reduced dimension drawings, which a lot of companies are going to? There are no basic dimensions. You have to query, and I can query anything I want. On the premium site video of this tip, I'll show you how these queries can be made. There are too many other things to worry about. Isn't it great? We no longer need to worry about how dimensions are placed on the drawing. If you are still struggling with old school dimensioning and tolerancing, give us a call. We can help. Because at Techies, you know the GD&T rules. I'll see you next tip. Here's another tip about what to do when datum features are modified at MMC or LMC. What you should not do is treat it like an additional tolerance or bonus. It allows a shift at the datum feature as the size of the datum feature changes. Here are a couple of parts from our product, which is the Intermec air clutch brake. This part has a pilot diameter that aligns it to the mating part, then 4 screws hold it together. The mounting face is our primary datum feature. The pilot diameter is the secondary datum feature. We're able to modify the pilot diameter at MMC because as the pilot diameter is produced nearer to its smallest size, it's allowed to shift a bit in order to get the screws to assemble. If our supplier treated the datum shift like a bonus tolerance, the clearance holes could be out of position more within the pattern. As a result, we might have to shift the part one way to assemble a couple of the screws, then take those screws out so we could shift the part the other way to assemble the other screws. This tip uses a simpler assembly to illustrate the point. On this part, datum feature A is the surface, which is the mounting surface, and datum feature B is this outside diameter of the cover. And the reason it's the datum feature is it does the locating of the cover when I assemble it to this case. If the outside diameter is made closer to its lower limit of size, I would be able to shift it around inside the case at assembly in order to get these screws to go in the clearance holes. And for that reason, I've put an M here on the datum feature. Now, that doesn't mean that I get more tolerance on the position of these holes. It means that I will allow a shift on the datum feature in order to bring these holes into their positional tolerance. If you treat it like a bonus, you're saying that the pattern can deviate more. In other words, the holes could get further away from one another or closer and kind of destroy the pattern. So that's not what it's saying. What it's really saying is the pattern can shift relative to the datum axis established by datum feature B, as long as we maintain the pattern. Here's an animation that shows the result if you treat that M as though it were giving you a bonus. Yeah, I can shift the part around at assembly, but if you gave a bonus to the position tolerance because of the M on datum feature B, I might only get these two screws to go. Then I could take those two screws out and shift the part down to get two screws to go here, but that would just be silly. So that's not what it means when you see that M on the datum feature. You can't give these clearance holes additional position tolerance. This animation illustrates why we allow the M on the datum feature. I can shift it around as long as the pattern is maintained so that I can get all four screws into those clearance holes. And I hope this helps everyone appreciate why you cannot treat that M on the datum feature reference as a bonus. There is a shift that is allowed, but the pattern has to be maintained. So, if you want to be able to assemble all of the screws in your product, be sure to deal correctly with datum shift. That's what we do here because at Techies, GD&T rules. See you next tip. Controlling a derived median plane on a regardless of feature size basis can be difficult to inspect. When the design allows, adding the MMC modifier can greatly simplify inspection. This tip will show you how. Prior to the 2009 revision of the Y14.5 standard, the control I'm about to show you was accomplished by using straightness associated with the size dimension. But as of 2009, we use flatness, and it does make a lot more sense. And it's saying that the derived median plane down through this feature has to be flat within 0.3. That would be true if there wasn't the modifier here. But because we have the maximum material condition modifier, it says, hey, only at the largest size, at 20.2, does it have to be flat within 0.3. What this does is it creates a boundary. So when I apply this, it overrides Rule 1. Without this flatness, this feature or part would have to fit through a slot at 20.2, also known as an envelope or a go gauge. By adding the flatness, we're saying, no, it can be bigger acting. Not bigger in size, but bigger acting than 20.2. So it could be at 20.2 and be bowed as much as 0.3. That creates a maximum material boundary, which is equal to the largest size plus the 0.3 flatness tolerance, which gives us an envelope of 20.5. So we just overrode Rule 1. We don't have to fit through that slot at 20.2 anymore. We have a new slot that's at 20.5. This becomes a single limit control. In other words, the only thing you have to do to check this flatness is make sure you don't violate that 20.5 envelope. So it could be done with a hard gauge, or another approach would be to master an indicator at the 20.5 value, and then when you run the indicator over the part, with the part sitting down on the surface plate, all your readings better go down. If any of them go above 20.5, this wouldn't have fit through that slot that I mentioned, or that gauge. So this is a way of simulating a hard gauge without ever building one. And the other advantage is you're getting variables data for process control. In other words, you can keep track of the highest points and monitor if your process is getting closer to 20.5. You can correct your process before you ever make a bad part. You still must meet size, however. But size is only checked now with a 2-point check, like a micrometer measurement. So I just have to verify when I use micrometers that it falls between 19.8 and 20.2 for point-to-point size. But then it could be out of flat more to make it act larger.
Don't make GD&T tougher than it needs to be. We can help you control your part geometry while you experience minimum pain, because you know that here at Techies, GD&T rules. I'll see you next step.
When designers and engineers don't use GD&T on a washing machine or cellular phone, I guess it isn't a big deal. The result is a lot of scrap and wasted effort at the company, but no one dies. What really ticks me off is when the folks designing medical devices, military hardware, and other products that affect life and limb don't do it right. Here's an example from a commercial aircraft. This is a case study of a part called a throttle pulley sector used on a commercial airline. You see it rotating here. It rides in 2 ball bearings, then on a shaft. When this actuator is moved, the throttle pulley sector rotates. These 2 cables go back to the engines, and so they control the speed of the engine. These guide pins are here to make sure that these cables never come off the throttle pulley sector. So the critical gap is between the throttle pulley sector radius out here and the guide pins. We don't want this to come off. And the way that is checked is with a no-go gauge. As long as the gauge doesn't go, the gap isn't too large. If the inspector misses that or doesn't check it all along that radius, the result is that these cables could walk right off the pulley. If that happens, the engines die, and, well, you can figure out what happens next. The original drawing looked like this. I've redrawn it, cleaned it up a little bit. But they had this radius of 7.064 directly toleranced. In other words, the plus or minus 5 down here applied to the 7064. The trouble is we don't know where the center of the 7064 is. You might guess that it's in the center of these bearing pockets, but there's nothing on this drawing to tell us that. Also, the bearing pockets were machined in one setup, and then they would refixture the part to machine the radius in another setup. So, oft times, the center of the radius was not right at the center of the bearing pocket. The solution is to identify these bearing pockets as your primary datum feature. As you can see here, I'm calling it datum feature A, 2x, so the 2 pockets establish a common axis that the pulley can then pivot around. On that critical radius and on these V-grooves, we have a profile tolerance of 10 thousandths. Now this 7064 isn't directly toleranced, it's a basic dimension, which means that's the goal. And the tolerance of 10 thousandths is on this surface with respect to the axis established by A. One way you might think about inspecting this would be with a drop indicator. I would master the indicator at the 7.064, and then I could either sweep the critical radius with the indicator, or I could hold the indicator stationary and rotate the part underneath the indicator, the way the part functions. It would be rotating about the axis of the two bearing pockets. And when I do that, the indicator could not move more than +5 or -5, because with profile, the number in the box is always total, and it's implied centered on the basic goal unless you're told otherwise. What could be simpler, and why wouldn't you do it this way? Because it only has one meaning, especially since this can affect life and limb. The entire shape of the end of the throttle pulley sector with the V-grooves could easily be checked with a simple fixture and an optical comparator.
Next time, I think I'll take the bus. If your products affect lives and safety, please learn how to control your part geometry with GD&T. The stuff that most engineering colleges do not teach. If you need help with it, give Techies a call, because at Techies, GD&T rules. I'll see you next tip. Here's another tip regarding how dimensions are placed on a drawing. A metrologist friend of mine calls it Compound Angles 101.
Keep in mind when applying basic dimensions, unlike directly toleranced or plus-minus dimensions, that it really doesn't matter how they're placed on the drawing from a design intent standpoint. In fact, many companies now are leaving the dimensions off and letting the supplier query the model. I see a lot of people locating holes that are at compound angles by locating one point or one end of the hole in space using 3 dimensions, and we see that on this drawing. First, let's check out our datum features. Here's datum feature A, and datum feature B is the hole, and then C stops the rotation, so that gives us our origin right here. Then we have this 29.2 dimension coming from our primary datum plane, and the 11.7 coming from the plane passing through datum feature B's axis. But we need one more dimension to locate this point in 3-dimensional space, and that is this 10 millimeter dimension. So now I've located this point in space, and then the axis goes off at this compound angle. This can be kind of difficult, though, when you have the part in your hand to actually find that point. Keep in mind that this 10 millimeter dimension is going to the surface, and that surface isn't going to be exactly at the basic location when you're holding the part. There's a profile of 0.8, which means that the surface could be 0.4 that way or that way. So trying to find this point in space can be difficult. A different approach is, once again, we have the same datum features here, but I've put the views so they're projected so that I can look straight down the axis of the 2 holes. So first we establish our origin of measurement, and then in my inspection setup, I would flip it to the compound angle, so I'd be flipping it twice, once to this 30-degree angle, and then to this 30-degree angle. But that would give me a view straight down the hole. So now the dimensioning becomes simpler. From my 0, 0, 0 origin, established by my datum features, I have the 78.7 dimension, and then the 14.3 and the 30 dimensions. But they're not locating a point in space, they're locating the axis. So I can then measure the holes to find out how much they've deviated from their basic location.
Thanks, Eric, for inspiring this tip. We are always looking for better ways to define and control part geometry, because at Techies, GD&T rules. I'll see you next tip. I receive a lot of questions accompanied by a drawing.
I often redraw them so that they are not a direct copy, but the concept may still be presented in a tip. This tip explains that you should avoid combining directly tolerance dimensions and basic dimensions to define a true profile. The only place in the current standard where it is acceptable and supported to combine the two types of dimensions is when tolerancing conical features. I redrew this part so that readers of the tip could not figure out who committed this error, but you know who you are. This drawing tried to mix tolerance dimensions with basic dimensions. You'll notice that this 36.11 dimension is coming from the edge of this datum feature B, which is a toleranced feature. That's not really what the drawing says to do. So this is not correct. This would be correct. If we look at the profile tolerance, it tells us that the profile is located with respect to the datums established by features A and B. So A is this face down here, and so that would give me a datum plane. And then B is this diameter, and that gives me a fixed axis. And since B is regardless of material boundary, the old regardless of feature size, whether this diameter comes in large or small, we're to center up and get that axis. So that would be this spot right here. That is a fixed spot that I can measure that basic from, and then see if this surface is in the profile tolerance. So there's my origin of measurement by the datums established by datum features A and B. This is not a fixed origin. Datum feature B could come in larger or smaller, and it's not fixed. So taking a closer look at the datum reference frame, we have three mutually perpendicular planes. This one is established by datum feature A, and datum feature B gives us an axis. So we would fill this diameter and get an axis. We'd be using what's known as the related actual main envelope. That axis is the intersection of two planes, two perpendicular planes. And here is my profile tolerance from that origin. So the 1608 basic is from that axis, whereas that other dimension, the 3611, would be coming from this spot on the surface of the datum feature, which is variable. So that would be wrong. Now, my second and third datum planes are free to rotate since we've only referenced AB. In fact, the feature we're trying to control here, you see, is datum feature C, but that's okay. What we would do is we would have to rock or rotate those datum planes with the profile zone until we could bring this feature into that tolerance.
We make certain the folks we train will not make mistakes like this because at Techies, you know that GD&T rules. I'll see you next tip.